Thank you, Howard, again. I'm back again. This time I'm going to talk about this, what with the early detections of stroke, what we are trying to do. Because as you said, there's a lot of things we need to work on stroke. And one of the things is early diagnosis. If you do the early diagnosis, then you can use your drug. Otherwise, it's no point of making brilliant drug, but we cannot diagnose the patient. But at the moment, what will happen, the stroke patient comes and then we go to the MRI and the CT scan, wherever is available, which one is available. And many of in the world, there are many hospitals that don't have MRIs. So what we are trying to do, is 2009, I bumped into some engineers, and we are working with the engineers to look at some biomarker. And one of the biomarker we looked at that, as you know, that glucose is the marker for diabetes. And at the moment that glucose is been, there are so many companies is making this glucose sensor where you can take a drop of blood and then you can measure this glucose. But what we are trying is with Professor Jean Jose, who is an engineer, we are trying to look at non-invasively glucose measurement through the skin using the laser. So that's work is been at this moment it is coming to the clinical trial. But this here I'm talking about where I have developed this method where we can detect some biomarker for cardiac diseases and also the stroke eventually. And this is the proof of principle studies I'm going to talk about. So what happened is in stroke, there are lots of, in cerebral ischemia stroke, there are breakdown of phospholipids, activations of catabolic enzymes, that is phospholipase, and then there are a series of markers released in the blood. And also cerebral ischemia is accumulations of lactic acid. When this oxygen is not there, that's anaerobic oxygens, and then they start releasing many biomarkers. And one of the more important biomarker is GFAP, glial acidic protein. And now in the clinical study also showed that GFAP is released after hemorrhagic stroke within hours, whereas in the ischemic stroke, it comes much later. So if we can detect this in some way, because at the moment GFAP you can measure in blood by ELISA, which takes time. So you have to send the sample to the lab and things like that. And also other biomarker is as 100B, PERK7, NDK. And then there is also release of ROS, free radicals and ROS and things. So what we are trying is that to find a method where we can detect those marker within few minutes, few minutes or something like that, yeah. So what we did is, that method is we use some rare earth ions. And rare earth ions is comprise the largest naturally occurring group in the periodic table. That is and highly electropositive they are, which is +3 and +. This is the lanthanides, which been used in MRI. This is the group of one of them. But this is one particular thing is some of the rare earth ions fluoresce. So we are using that property to look at this, some of the marker. And we detect this laser-based technology. When you excite those excite those rare earth ions, they fluoresce, and then you can see the emissions. So if you conjugate this marker with rare earth ions, they shift the fluorescence and then different wavelength. So that is the properties we have used, and then we patent this work. So what I'm going to do is the work. Our aim was analysis of metabolites with photodetect with rare earth ions, and then subsequent identification by collecting the photoluminescence spectrum when excited with a suitable laser source. So what our objective is, first of all, if we have to use it non-invasive, then you have to inject it to the patient. So what we are trying to do is test the toxicity of these rare earth ions in the cellular system. But our first target is looking at the in vitro. Take some blood and then do this technique, whether in vitro we can do. If you shine the laser, you can, within minutes, you can tell that's whether the spectrum has changed or not. And if it works, then we can take it to the in vivo model. And that's why we need to know the toxicity of these ions. And then our aim is phototag these metabolites, different metabolites with rare earth ions, and know which wavelength they excite. And also we have to decide on the laser wavelength. If you have to do non-invasively, we have to find the wavelengths where the skin is most transparent. So this with the rare earth leavening. And finally, they identify photoluminescence spectra, emission spectra of phototagged metabolites. And our long-term aim is to exploit this method, this optical transmittance of the skin and the blood vessels. Sorry, it's not working, I think. Right, so blood vessel for developing a methodology for minimally invasive analysis of key metabolites in stroke, such as GFAP and others. And for proof of concept, we use the lactic acid because anaerobic pathway, they produce the lactic acid. After stroke, they produce the lactic acid. And here you can see, sorry. Thank you. Yeah, thanks. Oh, this is the wrong one, I think. Sorry, it's gone to. Sorry, this slide has gone a bit. Yeah, right, okay. So, yeah. So this is, as I said, the toxicity. We have the talk about the cell viability of culture cell in the presence of europium nitrate. Europium comes in different form. We choose the europium nitrate and europium acetate. And by MTTSA, we have used that cells. This is the neuronal cell. And we have used the different concentrations of europium. And as you can see with the MTTSA, you can see this. In the presence of europium, the cell survival significantly increases up to the concentration of 10,000. Sorry, 1,000 is more, and up to 10,000, it's become toxic. And the same happens in there. If we keep it, this is for 24 hours data. But if you keep that cells, treat the cells for 5 days, this long-term effect, its effect is much greater in 10,000, but up to 1,000, it is quite safe to use. And we can use in that different concentrations within that range if we have to do the non-invasively. But at present, we are doing it, as I said, the in vitro model. And what we did is in here, also we find out that when you give the oxidative stress, we expose the cell in hydrogen peroxide and whether it is protective. And as we found that, because as you can see from there, we can see this cell survival is growing up to the 1,000. So what we wanted to find out what happened in the oxidative stress. And we found this oxidative stress, there's reduction of cells, but when we treat these cells in the presence of europium nitrate, treat this with hydrogen peroxide, the cell survival is better, and which is significantly increase the cell survival. So somehow these ions are protective. And what we think, we don't know what mechanism they do, how they're protective. But one thing is because these ions, as I said, they are strongly positive. So one is that 3+ and 4+, those ions. Europium is 3+. So they might do, because when oxidative stress, there are lots of ROS production. They are the minus so molecules, biomolecules is released. So one way probably these positive ions can bind with this negative and that way mop up some of the negative effect, but we don't know. This is our assumption. And what we did is to start, also we look at the skin, when is the skin is transparent, because we have to use the wavelength. So this is the published work, and this is the scattering of rodent ear tissue over visible to near infrared spectrum, and we can see the absorptions within 400 to 800. And if you can flip that chart through this 1 millimeter pig skin, we can see these skins are more transparent within this wavelength, 400 to 1600, about 1400, 1500. So this is the range where we can use the laser so that the skin are more transparent. So we can probably use that wavelength of laser to get the non-invasive detections of biomolecules. So this is our lactic acid. What we did is we conjugate this europium nitrate with the lactic acid in water and excite it with laser 395 nanometer excitation. And what we did is find is that we get the two peak. One is 592 and one is 616. And here are the different concentration, because different concentration of lactic acid we increase. So as we increase the lactic acid, this decreases the peak. And if we can find out the ratio, then you can tell that how much molecules are present in blood. And this is the curve, exponential curve fit. And as you can see, this is quite good sort of relationship. And then what we did is, because this is in water, but if you have to do it in blood, then you have to do it in the blood, whole blood and plasma and serum. When we looked at in the whole blood, we could not see anything because blood is so thick, so we can't see that. And when you get this 1 ml of blood or a few microliter of blood, the blood cells goes down, and it's difficult to see. But most interestingly, when we do it in the plasma, it's excited in the 39 point, and then we can see the same peak. This is there are two peaks. One is 592 and one is 616, these two peaks. But we don't know because there are some light probably is passing through, so I don't know why we get that non-specific thing. But when we subtract this, and we can see that inverse correlations, and when we increase this lactic acid concentration, and this is in plasma. So we can, nice correlation, we can see that one. And for some reason, this slide has gone up. And then we looked at in the serum as well. Oh, this should be the serum. I didn't. Sorry, the other one is serum. This is in the plasma. And in plasma, you can see this again, same one, 592 and 616. Here, this peak is gone down, this peak's gone up. But again, if we do this ratio, you can see this inverse relationship. So in plasma and serum, we can find out these concentrations of the molecules, lactic acid, what is present. And we also tried in myoglobin and troponin I for cardiac disease. But for stroke GFAP, we have not done it yet. So I am not showing it in here. So this is the method we have developed. And in future, probably we can use this technique, but it needs much more work on it. And my postdoc is working on that one. So that's the method we have developed, and hopefully we can apply to GFAP. So clinical significance of this result is that we can metabolite detections in plasma and serum, and also we chemical analysis the quantity and potential route for quantifications. We can quantify that how much is there. And then our long-term objective is the data analysis and suitability of laser-based spectroscopic technique for potential imaging. And this is another company is interested in, and we are talking with them. And probably we need to monitor key metabolites on human patient. And I'm talking to the clinician who is working with me. We can look at the ischemic versus hemorrhagic stroke and whether we can look at the GFAP. And next time, our final one, this target portable device for telehealth or GP surgery-based care, which our blood glucose work has been done as well. So this will be complementary to, this is not replacing the MRI or CAT or PET scan, but it will be complementary to, this technique will be complementary to all these scans and techniques. So, but it's a long way to go. Thank you very much. Sorry, I should not finish my talk without giving the name of these people who are working with me. Professor Jean Joseph, Professor Animesh Jha, they are the engineer working with. These are my postdoc. And Sabha is here, PhD. Nikita, she just finished her MSc. He is working on the blood glucose sensor. Nadira, she works on all the models. Pidusha, she did masters, and Dr. Trevor Batten. And we have that Queen Mary University of London, Pankaj Bhatgama, and postdoc Annabella. And Kirkstall Company is helping us, and Nurse Scientific Limited. And also we have funding from the BHRC, EPSRC, and also Innovate UK, BBSRC, and Yorkshire Alzheimer Research UK Yorkshire Network. So that's the funding body who funds my work. Thank you. And he is professor now at the moment, so it is in doctor in Asia, sort of. So thank you very much for listening. Nice. Any questions? Others? I'll move on to the next one if you do. Yeah.
Yeah, ma'am. Have you undergone the level of serum SOD level, serum superoxide level?
Yeah.
In the cases of infarct cases, have you undergone?
No, I have not done. That's why
that is again a biomarker.
Yeah.
Just to
superoxide. Yeah, that's the superoxide. But one thing is what we are thinking of. If we use that europium, that the ion we are talking about, they might reduce the superoxide concentration because they are all minus, and these are highly positive charge. Instead of binding, it might bind to this superoxide. But that will be good things. We can probably, that emission spectrum may change. And that way we can see the superoxide release and things like that. But this is very early stage.
Basically what I am talking about, that is the serum SOD level.
Yeah.
The superoxide dismutase level, that is the enzyme. Superoxide dismutase enzyme, SOD enzyme in the serum, not in the brain.
Right.
Because as and when a patient gets an infarct, the level of serum SOD level that decreases up to 5 days post-stroke day.
Right.
And then thereafter it increases.
Is it?
Right. Yeah, definitely. There is a paper on
reperfusion
in 1997, definitely.
Yeah.
That paper has been published in 1997 by M. Spranger et al.
Yeah, but it is after 5 days.
No. From first day up to 5th day, the level decreases in the serum.
Yeah.
And thereafter its level increases.
Right.
So that means the superoxides which are being formed at the level of synapse is being used up.
Yeah. Okay.
And then the level of SOD increases in the blood. So is there any correlation of all these things? Biomarkers and then...
But this we did not do it in the stroke animal or stroke patient. This is the human blood.
Yeah.
This is normal blood. We are trying to optimize our technique. So that's we are looking at that whether we can measure the biomolecule with this technique, so that in the hope that we can measure the different concentrations of biomarker in blood, and just after the stroke, immediately when you shine the laser and you mix blood with that ions and then shine the laser and you can see the reading. so that in the ambulance also they can look at this and then tell
non-invasively.
No, this is in the blood. They take the blood anyway to get the blood glucose. But if we have another sensor where we can measure the biomarker, that will be quite advantageous. So they can look at the blood glucose level and also the biomarker level, and at least they can start the preliminary treatment rather than until they come to the scan, MRI scan and things like that. So that is our method is quick, and it can be done with the laser. And this is Professor Jose, he is the sensor person, so we are working together, sort of. Yeah, but probably in the 5th days also people can use it, but that won't be as effective as just after the stroke. Yeah, okay. Right, yeah. Any questions? Right, okay, thank you. So I just... you want to ask? Oh, sorry, you wanted to ask?
Yeah,
oh, yes, sure this, yeah.
Is it possible to measure this concentration in tissue or in homogenates?
I don't know, because in blood we are having problem because it is too thick. So what we have to do, of course, we have to probably dilute the blood and to measure this marker. But if you want to non-invasively, you cannot measure that. So what we are trying to do is we like to combine. It's a much more difficult thing. So which we're trying to combine on Ediron. Have you heard of Ediron? This is very new things. This is the small protein against this biomolecule, and we are measuring this Ediron with europium. So it can increase the sensitivity so that we can measure this in the whole blood, and that's probably the other way you can do it. In tissue, we don't know. We have not. We tried with atherosclerotic tissue, and it's difficult because it's too thick. So we need to find something else which can europium binds to, and then we can measure. In vitro atherosclerotic tissue we tried. Yeah. Thank you.